Okay, I think it's time. Let's get started. Good afternoon. Welcome to lecture 10A. First, we're going to continue what we have left off yesterday on memory controllers. And after that, we're going to also, again, talk about memory controllers more, but in the line of how to improve service quality and performance. As you can guess, and you have actually observed also yesterday, memory controllers are doing a lot of decisioning, a lot of scheduling is happening. And whenever you have such kind of decisioning and scheduling, they can come at price of performance overhead, fairness overhead, quality of service overhead, and so on and so forth. So it's very important to look at that aspect as well, which we're gonna get to that hopefully soon. Any questions from yesterday? Okay, then I think we can jump into the lecture. So yeah, this was the slide that we were discussing about DRAM controller functions. I don't want to go over it again, but there was a point that I forgot actually to mention. So essentially, memory controllers need to handle, a lot of resource conflicts that we have, like banks, bus, channels, and try to schedule requests. But you should also understand that memory controllers does not schedule essentially requests saying that, oh, I'm scheduling requests from thread A or thread 2 or something like that. In the end, memory controller sends commands to the DRAM, because DRAM works with commands, and these commands like activation commands, write command, read command. So in the end, memory controllers, one of the important tasks is translate requests to DRAM command sequences. And that's the part that I forgot to mention, which we're gonna also see a little much more today about it. And this was one of the pictures that I showed about the function of the memory controller, that we have arbiter, also several banks, like queue for different banks, and then we need to do some essentially scheduling across these banks. Also, memory controller does a lot of signaling in order to communicate with the DRAM chip. Here also we discuss about different scheduling that we have per bank queue, which called as a local scheduler. And in the end, we also need to do some global scheduling, because there are some resources that they are shared globally, like the channel, for example. Okay, so I think we left off here. Essentially, DRAM scheduling policies can be quite different. There are different scheduling that you can think of. A lot of scheduling that we're also going to see today, in order to improve different metrics. But FCFS can be one, quite naive scheduling that basically it means first come, first serve. Essentially, you have a queue, and you schedule in a, on the order that you put things on that queue. So all this requests first. So you can actually also make it a little bit more intelligent by knowing basically the organization of the DRAM, that we have this row buffer. When we open the row and we move the row to the row buffer, then potentially we can, if we can address requests in that row buffer, we can actually address them with much higher performance and lower energy consumption. So that's why another scheduling policy, which can be actually considered as one of the conventional, or let's say a more, commodity scheduling, which used in different memory controllers, is FRFCFS. And it means first ready, first come, first serve. So we first try to prioritize row heat first. So if there are some requests in the queue that they can be serviced on the row buffer, we will schedule them faster, like first. And that's good for row buffer. And then if there is no, we basically go with the FCFS, which is oldest first. So essentially, the goal for this is to maximize row buffer heat rate, which in the end can maximize DRAM throughput, also reduce energy consumption, because you don't need to close and activate rows, repeatedly and unnecessarily. But at the same time, also, that scheduling is done at the command level. So there are also column commands, read and write, that prioritize over row commands, which is activate and precharge. So this is the way that we are handling row heat first. So in order to open a row or activate a row, you need to send row activation command, right? Which means we need to send activation, activate pre-charge or pre-charge activate. So those are the commands. However, if you have some commands in your table, which is they are like read command and write command, they are kind of column access, which means that you have opened a row in row buffer and you're addressing them with a column address. So that's why by sending these commands like read and write, you are actually doing this row hit first, and then essentially, if there are no, let's say, read and write command, we can do row commands. And within each group of commands, basically, we try to prioritize older commands. So if we have several, let's say, read and write commands, we do based on FCFS, which is oldest first. And also, read and write commands have some priority over row activation command in order to ensure row hit first scheduling policy. Make sense? Okay. So it's just a quick review that, I mean, you're aware of all these things. Basically, we have, here is a like DRAM bank with columns and rows. And so you send essentially row addresses, and then the row becomes available in the row buffer, and then you send column address, right? So if the next request is from the row 0 and another column, essentially that's a hit in row buffer hit, and you can basically schedule it or address it fast. And at some point, if you get a request from another row, essentially you need to close the row, meaning that you need to pre-charge the whole array and activate another row, and basically move it to the row buffer, and then start addressing that. So that's just a review about difference between row hit and row conflict. Okay, so essentially DRAM scheduling policy is in the end about the prioritization, how we basically prioritize different requests in different orders. So prioritization can be based on request age, like we can again consider as a first come first served, so first come first served tries to actually prioritize requests based on the age, so when some requests or commands are aged, basically we're going to prioritize them more. Can be also based on row buffer hit and miss status, which is FR. Can we also consider about some request type, which is prefetching, read and write. So for example, if you have different requests like read and write, remember that our DRAM bus is actually bidirectional. So we cannot really. So when we are doing read, we cannot immediately do write. So we need to spend some time to change the direction of that DRAM bus. So that's why when you want to schedule, you need to also consider about if this is related to the read operand or write. Basically, read request or write request. Or sometimes you can be also lucky, and because prefetch request also they're going to consider as a read request, right, in the end. But the processor can also tag them that's like these are prefetch requests. Try to address them or handle them as soon as possible, but basically you have more freedom probably. So you can also consider that, like memory controller, you as a memory controller, put yourself on the shoes of memory controller. So memory controller can understand that, this is a prefetch request, so how I can handle it. It can be different. We actually have done some works in the past, and it turns out actually at some point, you really need to prioritize prefetch requests. So the fact that prefetch requests are not requests from the real application, because prefetch requests, those are requests that you're generating in order to bring data, sooner from the moment that you need to the cache. So your application may not need it immediately, right? But in some cases, actually, you need to prioritize prefetch requests because that can actually provide much better performance at the long run. Also, requester type, load miss or store miss. These are different. Like from the processor, if basically the request that you're getting to read something from DRAM is actually coming because of a load miss, that for processor access, for example, cache L1 cache, and then miss in the cache, and then basically you're bringing data. Or it's actually about a store miss, that processor wanted to write to the cache, but that block was not available in the cache. And then now we have this store miss, which means that we need to bring the block from the memory to the caches such that we can store it, we can update it, right? So the thing is that usually when we have a load miss, that's actually much more critical path. So probably you want to prioritize load miss over store miss. So that's another, but store usually is not on the critical path of the processor, so you can delay it a little bit until some time. Also, request criticality is a very important topic. In general, how critical that request is depending on, which means that how much that request can cause installation, essentially. And you can think of one core, like a single core may provide a lot of different requests because of memory level parallelism that we have an out of order execution. One core can also generate a lot of requests. And these requests might be actually, they are not the same. Some of them are much more critical, meaning that they are at the, basically, if you don't address that request soon, the processor is going to stall. So that's one way of thinking about it. Or there might be also different cores that they are providing requests to the DRAM, and then they all share in the memory controller. So some of these requests actually are coming from some cores, which that core is much closer to be stalled. So if you know that information, you can try to prioritize those requests over some other requests. So request criticality is also very important. We have done some works, for example, in GPUs, that when we have different cores, different streaming multiprocessor in GPUs, they generate a lot of requests. And some of these streaming multiprocessor, they have less number of active threads. So when they don't have enough number of active threads, meaning that they cannot tolerate the memory access latency. So if we have that information at the memory controller level, we can prioritize requests from those cores such that we can cause less stall for them. Okay, all that's missing the core is also one of the example in out of order, for example, or how many instructions in core are dependent on it. Will it stall the processor, and so on and so forth. Another important point can be interference caused to other cores. Like when you want to prioritize one request, what would the effect of this prioritization on other cores? Think about, again, that, for example, read and write. Like there are a lot of cores that they need to do reads, and you have a write request from one core. So if you try to schedule that write request, meaning that basically you are delaying all these reads, essentially. And also consider the fact that that bus needs to be in one way. So that can cause some interference. Or, for example, think about that row buffer, hit rate or row buffer conflict. So there might be some other cores that they can actually benefit from row buffer hit rate, but by scheduling some other cores or some other requests, you can cause some interference to other cores, which we're going to see also a lot about this point when we talk about service quality and high performance in DRAM scheduling. And there can be also many other points that you can think of. Do you have something in your mind to add to this list? Okay. So, very quickly also in row buffer management policy. So when you open a row and you move data to the row buffer, you can actually have this policy that call it open row, which we keep the row open after an access. So the upside is that next access might need the same row, so we have row hit. And downside is that next access might need a different row. So now we need to pay for the overhead of row conflict and also wasted energy caused by keep the row open, right? So that's a trade-off that you can see here. On the other hand, you can actually have closed row policy, which essentially we close the row after an access if no other requests already in the request buffer need the same row. So basically, we don't need to be that dumb, that in the closed row, we immediately close the row. We checked the requests that we have already available in the buffer of the memory controller. If there are no requests that can be accessed by that row, we basically close the row. So this can be one way. And then, so of course, The upside is that next access might need a different row. So now we are avoiding row conflict because by closing that row, you are already paid the overhead of pre-charge. So that pre-charge latency actually has been overlapped kind of, And then while you get a new access, basically you just need to open another row. So you don't need to pay for the pre-charge and activation. You only pay for the activation command, right? But downside is that there might be some next access that can be serviced by the same row. So now you have this extra activate latency. So I think you can imagine that nowadays we have adaptive policy that essentially a memory controller can try to predict what would be the best. Should we keep the row open or should we keep basically close it? If we want to keep it open, like how long we need to keep it open? So there needs to be some prediction to understand the access pattern, which can be expected from that application or several applications that they're running together. This open row policy actually can also have effect on the read disturbance. Later on in our memory robustness lecture, when we talk about row press, you can think of actually we can do some programming and guide the memory controller such that try to keep the row open as much as possible. And if you keep the row open as long enough, actually you can cause read disturbance error to neighboring rows. So row press and RowHammer, they are different, but they can also be kind of combined together, because when you have row press by keep the row open, then your RowHammer, like how frequently you need to open and close a row to cause a hammer, that number would be much less. So you can actually, your hammer count would be in much lower number. In a very worst case scenario, can be by 1 or 2 access. So you keep a row open for a long time, and then only 1 or 2 access can cause error to the neighboring rows. Question? Okay, so in this table, I'm not going over it, but you can check it later. Basically, talk about different policy and how would we behave depending on the first access and next access and the commands we need to send. But I think you already understand the overall idea about it. So also DRAM has different power managements that memory controller should be aware of that and try to use this basically power management in order to save power. And also when put the DRAM or some region of the DRAM in some power mode, basically memory controller should change the mode also when the memory controller needs to access that part. So that's also another task the memory controller needs to be aware of that. There are different power modes. Like the idea is that when not accessing a chip, we want to power it down. But we cannot fully turn it off because first of all, DRAM is volatile memory. And if you just cut the power, then it's gonna lose the charge. You also need to do some refreshing. So if you don't do refresh, then also you're gonna lose the charge because of the limited retention time that we have in DRAM. So that's why we have actually different power states. Active, which is the highest power consumption. There are some other states like old banks, idle, power down, which you can think of reducing voltage and frequency of the of the DRAM. And also the lowest power consumption is when we put the DRAM on self refresh. And so all these actually power management. So you have different profile of how much power you are consuming. But at the same time, there are also overheads between transitioning across these power states. Like for example, put a DRAM on a self refresh. And when you want to make it active in order to access, you need to say, first of all, that would consume some energy. And also the performance, the latency you need to spend in order to change that mode would be also higher. So that's a trade-off analysis that in the end, the memory controller should do to predict that, does it make sense or is it worth it to put that DRAM region on the self-refresh? Because considering all the overheads, it might be better that, for example, we select, not the lowest power consumption mode. Maybe we just go with the old banks idle, or with power down, such that you don't need to spend a lot of time and energy to back to the active. But there might be some cases that your DRAM is going to be idle for a long time. So if a memory controller can predict that, then it's better to, for example, move to the self-refresh. So I'm just giving this to you, some, just to get you get some idea that how difficult it is for memory controller, to understand all these things and predict how we're going to access our DRAM. Because in the end, the memory controller also does not know what application, unfortunately, which you're going to see also later in this lecture, that actually the memory controller can also know and can learn, from the different applications that you are running. But for example, in our system, like imagine that our system is, we bought it from in 2020, and then the memory controller chip has been designed probably several years before that. And so back then, actually, the designers tried to optimize that memory controller and optimize the policies based on some workload set that they had. They did some analysis and they optimized the memory controller using some heuristic. And from that moment until now, we have many, many different applications, different workload, different users, and our memory controller is still doing the same thing as 10 years ago, right? So that's something that we need to think about it, how to change, and we're going to also see later today. Which you can start thinking about it also now. Okay. So I think by now you can think of kind of, have an idea of that why DRAM control is that difficult. But essentially, DRAM controller need to obey DRAM timing constraints for correctness. There are many timing constraints, like plus 50, which kind of underestimate. I think is more than 100 nowadays. There are a lot of timing constraints that we need to obey. Here, for example, some of them, like two of them, TWTR, which is a minimum number of cycles to wait before issuing a read command after a write command is issued. This is exactly what I talk about, like that memory channel bus is two-way, so you need to wait. You cannot immediately move from read to write. Another one is TRC, which is a minimum number of cycles between the issue of two consecutive activate commands to the same bank. Like activate to activate commands. So memory controller needs to keep track of many resources to prevent conflicts. We already discussed about like channels, banks, ranks, bank group, data bus, address bus, row buffers, and also need to handle DRAM refreshes, need to manage power consumption, and need to optimize performance and quality of service in the presence of all these constraints. So sometimes when you want to optimize for quality of service and performance, time to time you think, okay, we can do some reordering, like because we are in our queue, we are queuing requests in the memory controller, and for example, if you want to do this first ready FRF-CFS scheduling policy, which you want to prioritize those requests that can be handled by the row buffer. So you look in the queue, and if you see some requests that they can be handled by the row buffer, you basically reorder them, right? You move them to the head of the queue, right? So that's the reordering. But reordering is not that simple, because if you just do it like this, you're going to cause a lot of quality of service and fairness issues, which we're going to see also later. Question about this? Did I convince you that is a hard thing to do? Okay. So there are a lot of DRAM timing constraints, which I don't want to go over them. Like in this table, you can see some of these, like what they are doing and the symbol, and also the cycles that you need to wait. Here is also the paper that actually talk about something very interestingly. Like we talk about this, memory controller that should also get some information from the CPU core, meaning that essentially that the request is like a prefetch request or not, for example, or how critically is that request for that. But you can also benefit by making the last level cache aware of the memory controller. Like for example, in the last level cache, when you want to do this select, like exactly when in the last level cache, when you want to select a victim to basically forgot that. Anyway, so there are some blocks in the cache, and you need to find a victim and then move it back to the DRAM, and then you write another block to it, right? So that victim selection can be aware of the status of the memory controller. So which, if I can select a victim block that can be serviced by the memory controller faster, for example, that block can be handled by the first ready scenario, then that might be the better case, instead of naively victim based on LRU, for example. Or essentially, you can make LRU also aware of that status of the memory controller. So if you are interested, you can read this technical report. I think we haven't published this work, but there are some interesting study and idea in this work. If you are interested, you can check. Okay, so essentially, there are a lot of these timings for the DRAM that memory controller needs to obey them. So if you want to understand all these timings, one way is to check the datasheet of the DRAM that provide all this information, but it's usually terrible for understanding because datasheet. So the goal is not to tell us, why we have this timing. In datasheet, the goal is to say, what. Don't ask me the reason. Just make sure you obey these things, and that's the purpose of datasheet. However, in scientific papers, we try to say why before saying what. So that's why if you want to understand all these timings and why they are here, why we have them in the DRAM, you can actually check these papers. We provide almost the reason for each of these timings, and then we talk about how much you need to wait. But yeah, in this table, for example, you can see different numbers for different timings of the DRAM operations. Okay, and this slide actually you have observed before that essentially, when we want to activate a row, we basically starting from the pre-charge mode. After some time, we activate, and so with that, when we activate, that access transistor is activated such that essentially that capacitor is going to be charge shared with the bit line, and then at some point the sense amplifier kicks in and tries to basically amplify your bit line to the VDD, assuming that in the cell you had one. That this figure is actually based on that. But we actually have some kind of guard band. So this example actually can be accessed faster, but there are some rows because of process variation or some cells that they are weak or strong that basically you need to wait just to make sure that all of them can be serviced reliably. We have discussed a lot about this, so I don't want to go into it again. But yeah, basically, this is one of the reasons that, for example, we have this TRCD delay. And in TRCD, so that's a delay from activate until you can send the read command, right? So we don't have, for example, the command for sense amplifier. Remember the codec paper that we talked about? If we can, have some fine grain also access such that we can do activation for the sense amplifier for the pre-charge, then we can actually do some interesting things with the DRAM. But nowadays we don't have that kind of access. So essentially, you send the activate command, and internally there is an internal circuit that sends the sense amplifier enable command at some point. Paper SALP also, we have discussed many of these timings. I can actually talk about one of them, like this one, TWTR, which is write to read, which we already discussed, but it's not that easy. So it's not the latency between write command and the moment that you can send the read command. So essentially, you send a write command, and then you send a payload. So some of these timings, you need to obey them based on the bank level, per banks. Two ranks, for example, can share the same channel. But for example, in order to do this write and read, you need to have, you need to wait for that basically at the scope of the rank. Okay. Exactly. So this W here, it talks about goes into effect after the last. They are sharing the shared cache, but at the end, they are accessing these. Can you hear me? Okay. All good? Okay. So we had actually had an ambitious plan today, but it seems yeah, I don't know who, but someone doesn't want that ambitious plan. Yeah, environment maybe. Okay. Yeah, we have this heterogeneity, and so memory control needs to deal with requests from all these different requesters, which they are different in their nature also. So that brings me to this idea, self-optimizing memory controllers, because as we discussed, memory controller needs to do a lot of decisioning, and like designers, what they can do is actually they have some workload sets, some micro benchmarks, and using some heuristics, they can actually optimize the memory controller based on some metrics, essentially. But that design is very much rigid, you know, and after some time, you need to actually update it because of new applications that you have. Also, different users are different, the way that they use their system. And at the sometimes you want to improve, you know, apply some other scheduling policies, for example. You want to also consider some other metrics. So in the end, flexibility is very important. So now that's the idea of self-optimizing memory controllers, that you have a memory controller can basically learn from the workloads, from the characteristics of the workloads, and basically optimize itself, you know, as we go to the future. And they can learn and optimize as we go. So that's a paper from ISCA 2008. Kind of the date that I started actually my bachelor studies. It's so funny that back then I had no idea about how computer works, and people were just, you know, doing reinforcement learning for memory controllers. Yeah, but this work actually was very kind of forward-looking back then. Nowadays, there are actually, you can find a lot of works in our community and also other communities in ML, that people try to talk about ML for arcs or ML for system, you know, that they use machine learning for better systems, for better basically architecture. But back then in 2008 or so, no one was thinking really about such things. And this paper was really forward looking. And that's why also this paper has been selected in the 25-year retrospective of ISCA, which gonna be also part of your reading, I guess, in homework too. Okay. So reality is that it's difficult to design a policy that maximizes performance, quality of service, energy efficiency. So there are too many things to think about. We already discussed about them. And continuously changing workload and system behavior also is difficult. So our dream is to, wouldn't it be nice if the DRAM controller automatically found a good scheduling policy on its own? So that's the dream. This picture actually is from Rahul. He's not here, but I can say his name. Okay, memory control. So like this picture, basically memory controller needs to resolve many contention by scheduling requests. How to schedule requests to maximize system performance is an important you know, question to ask. So self-optimizing DRAM controller, the problem that we focus here is that DRAM controllers are difficult to design. It's difficult for human designers to design a policy that can adapt itself very well to different workloads and different system conditions. Because, I mean, how can they know, right? Like there's also the fact that in the end you do make some design decisions, but you don't know about the future. You know, you don't have that crystal ball to predict the future. So the idea is a memory controller that adapts its scheduling policy to workload behavior and system condition using machine learning. The observation is that reinforcement learning maps nicely to memory controller because I mean, we're going to see later the reason. And so memory controller can be considered as a reinforcement learning agent that, you know, makes decisions. And so if I have a picture of, yeah, here. So in reinforcement learning, essentially you have agents that makes decisions, some actions. So do some actions, and then basically we observe the effect of that action on the environment through some, basically the effect of that through some reward function. So that's with that reward function, we can actually learn and tune our decision, our actions essentially. So this can be also nicely mapped to the DRAM controller by considering that, okay, DRAM controller can be one agent, and environment can be, the whole system. We make some action, the memory controller, meaning that action can be, scheduling which command, essentially, some commands that we schedule. And so we get some information through the, some updates in the environment with the effect of that decisioning. And based on that reward function, we can actually optimize our decision to be, how good we are making decisions. Yeah, so for example, reward function can be data bus utilization, how good you are utilizing your DRAM bus, the data bus, for example. Okay. Also, the agent, which here, for example, can be DRAM controller, needs some states from the environment to, with those states, you can actually make decision. So for example, the states can be, we're gonna also see the set of states, but for example, the, like related to some of the cache hit, cache accesses, number of accesses in the cache, the miss rate that you have in your caches, or many other things. We can also think of criticality of the request, all these things that we discuss, that memory controller needs to think about them to schedule request. Okay, and also the goal here is to learn to choose actions to maximize, the data bus utilization. So that's a reward function that we design. So you can think of, reward function that you want to have immediate, the reward, or you can think of reward function that provides some history, in your action. So sometimes actually in such cases, when DRAM controller makes some decision, you may not get, immediate reward. You might get, but there might be also some reward that's causing, from future or from the past. So that's why in your reward function, you can combine this information through this formula, which is kind of weighted, formula. That for that you can actually combine, your reward from the now and also in the past. Sorry, in the future. Okay. So that's the idea of self-optimizing DRAM controller, that you can dynamically adapt the memory scheduling policy via the interaction with the system at runtime. So we associate system states and actions with long-term reward values. Each action at a given state leads to a learned reward. And the scheduled commands with highest estimated long-term reward value in each state. So that's the idea that I already discussed about the reward function. And we continuously update reward values for state and actions pair based on the feedback from system. So in this work, actually, we use a queue learning, like old-fashioned reinforcement learning, that you have a table of state and actions. But there are some other ways of doing reinforcement learning. For example, using deep neural network, like Rakesh and Gagan. They use deep reinforcement learning, for example, for other cases like in hybrid storage, which we're gonna also discuss it a little bit. Okay, so yeah, that's the paper. And yeah, here I want to talk about this, some of these state attributes. So for reward function, for example, we have this +1 for scheduling read and write command, and 0 at all other times. So whenever you schedule something, you just +1. So that is good in terms of the goal that we had. We wanted to maximize the utilization of the bus. So as long as you are scheduling read and write commands on the bus, so you are utilizing that bus essentially. So for that goal, this can be a good reward function, but you can argue, depending on some other scenarios and other metrics, this might not be ideal. So you can also, there is room, of course, for optimizing this reward function to consider many other metrics as well. For a state, for example, you can have number of reads, writes, and load misses in the transaction queue, number of pending writes, reorder buffer heads waiting for reference row. Like this shows, for example, how critical that request is. If the core is stalled or is gonna be stalled because of this request. Also, request relative reorder buffer order. So all these information, if you map them to the, put them as a state attributes, the memory controller can learn, from them, can use from them in order to make actions. So there are different actions that you can think of, like activate, write, read, which can be also, we try to separate between load miss and store miss for the read command, and pre-charge, and also pre-charge preemptive, which I think I don't remember now exactly what was the difference between these two pre-charge, but yeah, you can also check the paper. We also have this no op, which is do nothing. So it's also good for such techniques, that you also have an action that you do nothing, because if you have to do, if you also only have these actions, then you need to do something. And when you don't have anything, for example, you say that, okay, I'm closing the row, for example, right? So you always need to do some actions. So that's good to also have an action, which is you do nothing, which is no op. So that can provide, better, efficiency in the algorithm. So in our evaluation result, we show that we have large, robust performance improvements over many human-designed policies. So we compare, against many, human-designed policies, from prior work, as well as also some human-designed policy that we come up with using these, state attributes in order to make the comparison fair. But we actually show that, RL can actually provide better performance compared to human design, which even use all these state attributes because of the different way of designing in the end. Okay. Yeah, so this is a self-optimizing DRAM control. Of course, it's, as a plus, it has continuous learning in the presence of changing environment. And it also has reduced the designer burden in finding a good scheduling policy. Basically, designers specifies what system variables might be useful, for the state, and what target to optimize, but not how to optimize it. So designers still needs to pay a lot attention to how to perfectly or good design the reward function, because that reward function can play, very important role in the performance of RL algorithm. But in the end, designer does not need to deal with, how we need to optimize. So that's the beauty of using such techniques. But of course, how to specify different objectives, different metrics that we have that we want to specify for it. And in the end, like how we design this, the reward function is not easy. Hardware complexity also something, because like in this case, for example, we have this queue learning. So you need to store a table of states and actions. And that table can be actually costly, that can consume significant area. So in this paper, actually, we discuss, how we can reduce the area overhead of that by using techniques like quantization, with some generality that you don't store a lot of bits, for different states. So there are ways to reduce overhead, but in the end, you need to pay some cost, for that table. So other also way of doing reinforcement learning, for example, using DNNs, they also have other complexity. For example, they are not that timely. So it's very hard to use, for example, deep reinforcement learning that we use DNN for such decisioning that you need to do it fast. But for some cases that you have much more slack, like for example, handling storage, managing storage system, then you can, for example, think of using those, deep reinforcement learning techniques. But in the end, you're gonna have some hardware complexity, but you should also consider that, is there basically we need to spend some money, to get something. It's not a free performance improvement. But one of the actually important issue, which I think actually it's kind of limiting, the adoption of such techniques, is actually design mindset and flow. So in many cases, designer, they want to test. The testability is one of the important part of the design flow. So when you have such techniques like self-optimizing, like using machine learning essentially, so you don't have enough explainability, in the machine learning design. You don't know why it's getting proving performance. It's very hard to come up with a workload set, that you can check. If you, as a designer, if you're designing some things, some components, like in a old-fashioned way, so what you're designing. Okay, I'm adding these tables, I'm implementing this algorithm, and I know exactly what that algorithm should do. So I can actually come up with some micro benchmarks, with some workloads, such that I can test the function of what I have implemented, right? But unfortunately, in this domain, that when you use machine learning, you don't know exactly how actually RL is handling that complexity here for you. So it's very hard to understand that. And also, it's very hard to come up with some benchmarks, such that you can test. You can actually test each component of that RL, separately. But if you want to come up with some test bench at the high level, it's very hard. And that's something that kind of limits the adoption, and is actually kind of interesting research direction that people are trying to do in order to, improve the make this ML for arcs more adopted, because you need to think about how you want to test it essentially. And debugging is also very important here, which is hard. Okay, so that's about this paper. And this retrospective of this paper, if you are interested, you can also check. There are, other works, on this line. This is one of them, which I don't have time to go over it, but you can also check some, ongoing, some other works on, self-optimizing DRAM controllers. But actually, this, talks about some more another, like a more general domain, which is self-optimizing data-driven computing architecture. Remember that we discussed about data-centric, data-aware, data-driven, and this is kind of data-driven architecture. So instead of being human-driven, which human designs design the policies, how to do things. So many simple, short-sighted policies all over the system. We can actually do better. So we can have fundamentally intelligent architectures that is more data-driven, that basically machine learns the best policies, how to do things. And this is sophisticated, workload-driven, and changing and far-sighted policies. But of course, we need to rethink the design of all controllers. So it's not only memory controller. We have, controller at different, stage of the system. We have cache controller. We have storage controller. So all these, there are many, many other controllers. There are many decision-making in the system. And you can think of using machine learning for them. But at the same time, also, you need to think about how you coordinate between them. So similarly also in human way, like when you have different controllers in human design, you need to coordinate these controller. But in RL also, people are trying to use kind of multi-agents, such as these agents are coordinated each other, such to optimize the system. Yes. Yeah. So you might you will do some hardware description. You will use that hardware description language in order to synthesize and see the overhead, for example. Like for example, we wanted to see how large that the overhead of that Q value table. For that, you need to use some synthesizing tool or use some other tools like the memory compiler. For example, some tools like Cacti that you can estimate the overhead of that. So not in such works, we don't need to necessarily actually implement. You can actually do simulations, but in reality, if you want to build it, you need to go through the whole design tool chain, right? So you need to have some HDL that you program it, you test it, and then you synthesize it, and then you do post-synthesis simulation, and then when you're okay, you do place and road, and then you simulation after place and road. So there are all these things that you need to do when you want to design, and that's why testability is very important, because you need to test at all these stages. Mm-hmm. Yeah. Yes. Because of the performance. That's a very good question. And actually, we have such kind of things actually for storage. For example, in the storage controller, you have a multi-core there, and then a lot of these policies are running on the software, which we don't have access to it. It's kind of closed from the vendors. There are also some kind of open channel SSD that you have. You can actually change that software. But in memory controller of the processor, we need to be much faster. So there are some actually kind of microcoding, that you can use, for example, to change the timing. That's why we can actually change, with DRAM Bender, we are able to change some timings, Also, in some of our works, we show that you can actually change some of these timings by changing programming the BIOS of the system, right? But that's all about it. You cannot really change all the algorithm, do another programming, another software for that memory controller. The main reason is the performance. You need to do it fast, and you really need hardware. Well, that's hard to quantify, but my gut feeling would say that if you have a hardware that does something for you, and then you want to, instead of using that, you add a core and you run a software on that core, I think you're gonna see a slowdown of at least, it depends on the function again, but I think something 2 orders of magnitude is something that you can consider, you can assume here. But that takes it with a grain of salt, because depending on how sophisticated that function would be. Sometimes your function is so simple, which in the end, if you run a software, also software does not need to do a lot, So it's good to have so you don't see a lot of difference. But if the function is so complicated, then the software, you need to run a lot of instructions, but hardware can also easily do, for example, with some accelerators. Yeah, and that's why actually people are designing accelerators for for machine learning, because it's important to accelerate things. But very good question, actually. Later on, when we get to the processor-centric part of the course, we're going to get to the coherence protocol. And back then, that's in the coherence protocol, also, we're going to also see that trade-off. If you provide some programmability, you are able to change the protocol. You can actually update the protocol on the fly. But that comes with some overhead, which we're going to discuss it also later. Okay. So yeah, this is a self-optimizing memory controllers. But we use also this kind of reinforcement learning for other stuff, other parts of the system. This work, Rahul, for example, use reinforcement learning for prefetching in the L2 cache. Here also another work from Rahul that he used a simpler, actually, machine learning model, which is perceptron, to design predictor to predict that, when we have a memory request, when we have a DRAM request, when we have a memory request, if that request is gonna hit in any of cache level that we have, or it's gonna miss in all of them. So if it's gonna be a miss in all cache level, in L1, L2, and L3, based on our prediction, we can issue the off-chip DRAM access, faster, and that can basically reduce a lot of some part of the latency of getting data. This work was I was discussing about it. Like you can also use it for other parts of the system in hybrid SSD. When you have in your storage system, you have different SSDs with different characteristics. You can also now how you map your data, how to migrate your data. There are a lot of decision making here, and you can also potentially use machine learning for that. So this work we use. Machine reinforcement learning, deep reinforcement learning for data placement for hybrid storage. Okay, so in the end, so architectures for intelligent machines should be data-centric, data-driven, and data-aware. We have seen actually all of them. Like we're gonna also see more, but data-centric is we discuss a lot about PIM, how to do processing memory, also processing storage. Data-driven, we just discussed it, and data-aware, yesterday we discussed, for example, this work, Eden, that you can make the system aware of the, characteristics of the application. Okay, so I don't want to go over these things again, because I think you have seen these slides before. So yeah, maybe if we design our architectures more in this line, we're gonna get closer, to how our brain works, because this is kind of very amazing and very energy efficient. And the brain does not also differentiate between storage and computation. So the storage and computation actually is kind of very much distributed and data-centric. Okay. So if you want to learn more about intelligent architecture for intelligent computing system, I refer you to this paper and also some talks on this line. Okay. So there are some now, I'm flashing some slides regarding memory-centric computing because I want to get to this self-managing DRAM to show that how we can actually make the DRAM controller a bit more, memory-centric. Because the memory controller, from the part that we already discussed, is actually very much processor-centric, and also DRAM. The relationship between the memory controller and the DRAM is very much processor-centric nowadays. So with this work, we're gonna break this, dependency a little bit. Okay, I think we should take some break. Let's be back at 2:30, and then we will continue. Okay, let's continue. Am I audible? So with that introduction, I want to briefly talk about this work, self-managing DRAM. So this is a paper that's from Hassan and Ataberk. This paper finally got accepted in Micro 2024 after several rejections, thanks to the people that they found this paper disruptive. Maybe because it was disruptive in the processor-centric mindset, yes, it was disruptive in that sense, that want to, change the way that people look at the system, but in the sense of overhead is actually very much lightweight, and you're gonna see. So the thing is that DRAM interface nowadays, so we have this memory controller and DRAM chip, and we have DDR-X, for example, interface. And the memory controller send commands, and DRAM chip basically responds, with data, for example. So a memory controller essentially orchestrates all DRAM operations by sending these commands, and DRAM chip only execute these commands. And essentially, the interface is completely controlled by one side. So DRAM chip does not have any autonomy, if you will, on its own. So only DRAM chip. I don't want to use the the word, but essentially, memory controller talks to DRAM chip, and DRAM chip only says yes, sir. And that's what you need. And basically, DRAM chip cannot make decisions on its own, cannot talk to memory controller. Because that's very, against a processor-centric mindset. You want people are not allowed to talk to the processor. Only processor are allowed to talk, to different components. I'm not kidding. that's the mindset that we have in our system. Everything should come from the processor. But yeah, essentially, there are a lot of DRAM maintenance mechanisms like data retention, because of the retention error that you need to do refreshing. Also, because of RowHammer that you need to apply some RowHammer mitigation techniques. And there are essentially a lot of these maintenance mechanisms. And DRAM failure modes necessitate maintenance mechanisms. So these operations needs to be performed to maintain DRAM data integrity. But unfortunately, the thing is that DRAM chip does not have any control on them. Like memory controller needs to send these commands, like the refresh command, to the DRAM chip, and to DRAM to handle these things. And essentially, because of the density that we are scaling, we have much more error rates. So continued DRAM process scaling necessitates new efficient maintenance mechanisms. So we need to design more techniques in order to avoid provide maintenance mechanisms. So now the issue is that by considering the DRAM standard, it's very hard to progress. So essentially, we have this JEDEC, which is Joint Electron Device Engineering Council, which has more than like 390 companies, including DRAM manufacturers, parts manufacturers, system manufacturers, foundriers, and all these things. They basically define some standards and make sure that we design components that they obey these standards. So there are a lot of policy going on here that all these people need to meet, discuss, to come up with some standard. And as a result of that, things are very slow, until they can be adopted in this standard. So adding new or modifying existing maintenance mechanisms requires lengthy modifications to DRAM specifications and other systems components that obey the specification. So because DRAM interface is rigid. So that's why actually from DDR3 specification to DDR4 specification, it took 5 years. And from DDR4 to DDR5, it took 8 years. So a lot of several years, like multi-year effort by the JEDEC committee to apply or change the standard and to enable some of these techniques like mitigation techniques. Like in DDR5, for example, we have introduced 3 maintenance techniques, like same bank refresh, which improve bank level parallelism, refresh management, RFM, to improve robustness. You're going to learn more about it in our DRAM robustness, memory robustness lecture. And also in DRAM ECC scrubbing, such that we scrub the DRAM and essentially fix errors, in a periodic way. But actually, all these techniques took 8 years to be adopted. However, all these techniques actually could have been released much earlier if we were not dependent on this standard, essentially. So the problem is that introducing new maintenance operations takes a long time, because it will take a lot of time until in this JDEC committee, they agreed to basically to support that in the new standard. And it's not only one thing that they want to do. So there are a lot of things that they want to do, or they may not want to do. So in the end, it will take a lot of time to make decisions. So our goal is to ease and accelerate the process of implementing new efficient DRAM maintenance operations. So the key idea is that, like the key observation is that, so we can categorize DRAM operation into 2 classes, like access, which perform to serve memory requests, uses information available only to the memory controller, like the load address, store data, and so on. However, we have maintenance operations that perform to maintain DRAM data integrity, and this uses information available only to the DRAM chip. So then why not use the DRAM chip to do maintenance operations on its own, right? So that's the idea here. So the key observation is that a DRAM chip could maintain itself. So DRAM chip does not need memory controller to to tell itself that make sure you are maintaining yourself. So DRAM chip can do it on its own. So there are 2 benefits of DRAM chip autonomously performing maintenance operations. So one is that maintenance mechanisms can be implemented more easily and rapidly. DRAM interface modifications are not required to support that. And the second one is that enable DRAM manufacturers with breathing room to perform architectural optimizations without exposing DRAM internal proprietary information. So that's another thing, that essentially DRAM manufacturers, also they have much more room now for optimizations. So the solution approach that we have here is that to enable autonomous maintenance operations. So the key challenge is that DRAM interface is too rigid to accommodate autonomous DRAM maintenance operations. So from the processor and DRAM interface design scale, we have DRAM chip. So we are actually kind of here. So very, very much processor-centric control. If we want to do it completely at the DRAM chip, it can be DRAM-centric control. But we are not there. We are here at the processor. So the goal is to make a simple one-time change to the DRAM interface that enables autonomous maintenance operations. So this work, self-managing DRAM, SMD, the key idea is actually very simple. So memory controller sends some command, but DRAM chip is already doing some maintenance. So now the DRAM chip is basically allowed to, Yeah, exactly. So now the DRAM chip is allowed to basically, while doing some maintenance, DRAM chip can send negative acknowledgement to the memory controller. Like memory controller sends some requests to the DRAM chip, and DRAM chip is already doing some maintenance operations. Now the memory chip can just say to the memory controller that negative acknowledgement. I'm sorry, I'm busy with some refreshing, for example. Try again. And that's the whole thing we are proposing here. And some people actually, find it disruptive to the interface. But that can make a lot of difference. Like the key mechanism is that to reject access and activate commands. So, but of course there are a lot of details in the paper, like what would the granularity that you can reject. So because you don't, so in which granularity you are doing maintenance. So you can think of, we lock some part of the DRAM, like several subarrays, And then for that several subarrays, we are doing some maintenance operations. So we are rejecting commands that they are going through those subarrays. Also until when we are rejecting. So there should be also some threshold for that. So we are not going to, so DRAM control, the memory chip is not going to reject, requests forever, because we are not going to do maintenance forever, right? So there are a lot of discussion about that also in the paper. So DRAM chip controls in DRAM maintenance operations, and this with a single simple interface change that DRAM chip can send this negative acknowledgement. So for this, you can actually also think of adding a new pin, for that specifically to reject some requests, or you can also repurpose some of the pins that we have. For example, we actually have a pin used for alert. Like DRAM chip can send some alert command to the memory controller. I don't know about details of that, but you can actually also use, repurpose that pin for sending negative acknowledgements, for example. Okay. So now memory controller can orchestrate all access operations, and DRAM chip can now also perform its own maintenance autonomously, which now we have a nice partition between the memory controller and DRAM chip. And in the end, now the memory controller and DRAM chip are more like an equal partner. Like they, the basically relationship between memory controller and DRAM chip is actually both sides. So they really, the kind of request reply that they talk to each other. And DRAM chip is not the unit that always needs to acknowledge or accept whatever memory controller says. So SMD provides performance and energy benefits comparable to the hypothetical system without maintenance while improving system robustness. Details are in the paper, you can check. So benefits over the baseline systems attributed to overlapping the latency of maintenance operations with useful access operations. So now that DRAM chip are capable of doing maintenance operations on its own, memory controller can actually overlap latency of maintenance operations with also access operations that we have. And also it reduces command interference and energy use. So memory controller does not issue maintenance commands. And that also comes with energy and performance overhead. So that's a conclusion about this work. So new maintenance mechanisms require changes to the DRAM standards, which is quite slow. With this negative acknowledgement, we can actually make it more, we can provide some breathing room to the DRAM chip, that people can support many optimization techniques inside the DRAM chip without waiting for these things to be adopted in the standard, essentially. And we showcase high performance and energy efficient based on different techniques. And basically, our hope is that SMD enables practical adoption of innovative ideas in DRAM design and inspires better ways of partitioning work between processor and DRAM. And here is a overview of one of the sections in the paper. I'm not going to read it. You can read it, at home. But essentially, here we talk about like with SMD, we're going to be with more. Instead of being completely controlled by one side, meaning memory controller and DRAM, it's going to be fully request deploy, which is equal partner interfaces. Okay, so here's the paper, and also a talk from Hassan that you can actually also watch it if you are interested to learn more about this work. Question? Okay, so now I want to quickly go over memory interference, but actually it's much more related to the second sub-lecture that we're going to start today. So I will go over these slides actually pretty much quickly because we're going to actually also see a lot in the second part of today's lecture. So essentially, inter-thread and application interference, the problem is that threads share the memory system, but memory system does not distinguish between threads request. So, and if you know about like also this shared programming model, essentially you are different threads that they are working on implementing one application. They are sharing some part of the address space, like the virtual address space, And this can be also shared in the physical memory, physical space as well. And so designing the system which is not aware of that sharing actually can cause a lot of issues. So these threads can be related to each other and can be also unrelated to each other, can be threads from different applications. And that can also come at the price of quality of service and fairness, low performance, bad energy efficiency, and so on and so forth. So existing memory systems is considered kind of free for all. Like this is a shared resource, which is free for everyone. And is actually like without any kind of control. So control algorithms trade unaware and trade unfair, which we have in our memory systems. And aggressive threads can deny service to others, and that's a big issue here. So when you just put, the resources like free to all, there are some threads that they are more aggressive, like they are more powerful, and they may actually starve other threads. And it's not only in memory system. You can also think it in real life that we are having these issues. Okay, so do not try to reduce or control inter-thread interference. Also, another thing we have in our existing memory system. Basically, they do little things to reduce or control the interference we have across different threads. So uncontrolled interface, this can be, for example, an example that, the different, we have cores, multi-core chip that different threads are run in these, for example, these two cores can be actually two different single thread applications. And then they are actually sharing, some part. I mean, some level of cache can be private to some of these cores, but some level in the end are going to be shared. Interconnect also can be shared. So with all these share, you can lead to some unfairness issues. Assuming, for example, we have two applications. There's one of them is application that have stream memory accesses. You can think of, for example, application like vector addition. You have two vectors and you want to add all these elements. So this application, the access pattern is very much a stream. You are streamed through the memory to bring all this data to the processor to do that vector addition. And random application you can think of many different things because we don't have. So in many of applications that we have nowadays, actually they have a lot of randomness in their accesses. So the problem is that the stream actually both of them provide requests. However, the request from stream application can be serviced faster, and you can actually imagine why. And that is actually because of the way that memory controller handles. Like if you think about FRFCFS, first ready, first come, first serve. Requests from stream application, they're gonna hit in the row buffer because you open a row and you're streaming through that. So you're gonna send several column address, for that stream, and they're gonna hit in the row buffer, and as a result, they are prioritized. So and requests from the random, the access pattern, they are deprioritized, and in the end, you're gonna see the unfairness in the service rate for these two applications. We actually try to test it with some micro benchmarking. We call it a memory performance hog, and so here we have two different code segment. Here we have kind of a streaming access, and here we have a kind of random access. Like the index that you are accessing through that array is actually random. If you want to actually make it even better, it's much better to generate indices outside the loop. So because you don't want to pay the cost for the randomization function, because that rand function is actually quite slow. And by having this function in your loop, you are actually causing some noise in your study. So it's better actually to do this, generate all these random accesses outside the loop and put them in a array, and just access that in order to get your indices. Here also the same. So you can generate all these indices outside the loop, and then access based on those indices. But overall, like the understanding here is that our accesses here is a stream. Like we have sequential memory access and very high row buffer locality, like 96% hit rate, and is actually also memory intensive. In random, we have random memory accesses because the indices are random. And so as a result, we have very low row buffer locality, like 3% hit rate on average. And similarly, memory intensive because we are issuing the same number of memory requests. So now the problem you can imagine. So we have a request from thread 0, which is a stream. So we first, for example, address this one, and then we get requests from other threads, like thread 1, which is random. But in the meantime, also we get requests again from thread 0. And that's because this one has row locality, you are basically picking up that one. And you are piling more requests from thread 1, but you are not addressing them because you are getting requests from thread 0, which you can address from your row buffer. And that's why you keep scheduling thread 0. And thread 1 is basically is not scheduled. So there are a lot of animations here. But so assuming that, for example, row size is 8 kilobytes and cache block size is 64 byte, you can, for example, have 128 requests of thread 0 service before thread 1, because all these cache blocks can be read in a string manner, and all of them are hit in the row buffer. So essentially, you don't schedule thread 1 at all. Make sense? So as a result, this can actually cause unfairness. So this analysis on real application, we test MATLAB and GCC. And basically, we report different slowdown of this application compared to the case that they run alone. Like you run MATLAB alone on one core because it's a single thread, for example, single thread program. You run on one core completely alone, and you get some performance. And in second time, you run MATLAB with GCC, and then you get another performance. And if you divide the execution time in the shared to the execution time of the alone, you get the slowdown metric here, right? So you can see that MATLAB, when you run it in the shared mode, it's gonna slow down only, a little, 1.07. However, GCC is slowed by 3 times, more or less, which shows, how unfair slowdowns can happen in our system. So a row conflict memory access takes significantly longer than a row heat access, which we know, and the current controllers take advantage of the row buffer heat. So that's the commonly used scheduling policy, which is FRF-CFS. We have this row heat first and also oldest first at the second time. The thing is that both of them are actually unfair. So if you have row heat first, I think you know by now that how can this cause unfairness. If you also do oldest first, then you're kind of prioritizing application which is more intensive, because that application is, sends a lot of requests, which the likelihood of that application be always the oldest is more, So that can also be quite unfair. So that's why actually FRF-CFS is very unfair, and because basically it's not very good strategy for quality of service. Okay, we also, run the same, effect of this memory performance hog using our micro benchmarks that I showed for a stream and random. And we kind of actually observed the similar results, for the MATLAB and GCC that we had. So that can potentially basically suggest the reason that why we are observing that kind of behavior in MATLAB and GCC, for example. Okay. So you can also test like this virtual PC. So this work has been done when Professor Mutlu was in Microsoft. So back then they also had this virtual PC for Microsoft that they wanted to see the performance. So that's why it's one of the workloads. Okay. And it's gonna be a great, more important problem, like greater problem when you have more cores, as you can see here, that is quite vulnerable to denial of service. So the thing is that it's not only the problem of, so unfairness, you can actually argue about it, like, because it's very hard to say what is fair, right? And there might be also some applications that you really want to also prioritize, you care about them. You want so those applications to be faster. So ideally, if the memory controller tries to schedule requests in a fair manner across these two applications, that might not be ideal for you, because we really wanted to prioritize some other applications. So being fair actually is kind of arguable. But the problem is that once you have such characteristic in your system, malicious people and malicious program can also comes to play. Like there can be some people that they design attackers by using this kind of a strategy to cause denial of service, for example. Like assume that the attacker knows that your memory controller does FRF-CFS, and you are running a lot of applications on your personal computer, like GCC, like virtual PC, and then attacker can actually write the code with a lot of streaming access, and that the streaming access can run beside your application, and you're gonna see a lot of very, very bad performance for your normal application, right? So it's not only the performance overhead problem or fairness. You should also think it about more deeply, which can also lead to, in the end, a denial of service attack, which puts it in another level. So that's why actually this work has been presented actually using security. That Professor Mutlu presented this work. I think back then this work was one of the work that was very much at the low level, at the low hardware level. Because usually in security domain, people are, back then they were much more focused on system software, let's say. But nowadays, because of this RowHammer and things similar, that a lot of people in security domain also trying to, work on low level domains, under for different attacks and defenses. Okay, so yeah, so with that, you're also unable to enforce priorities or SLA, that service layer agreement, I guess. Essentially, the priorities that you have, and also in this also it can also lead to a low system performance. So in the end, uncontrollable, unpredictable system, which is not good for anything. Also, because it's not only the fact that it can actually lead to a low performance because of the fact that there might be two requests there. One of them is a stream, which is quite memory intensive, and there is a lot of requests. So FRF-CFS is going to actually prioritize that. And there is also another thread which generates time to time some requests, but those requests are not that many. So meaning that application is much more compute bound. That application actually is the application that can utilize the processor core a lot. But by not addressing the request from that application, you're also causing low utilization rate on the core also. So that memory intensive application, like the stream with the streaming access, probably actually the core is not utilized already, because that application or that thread is already waiting for a lot of memory requests coming from the memory. So the core is not going to be very much utilized. But the other application might be able to utilize the core, but it cannot because of the fact that we are not servicing those little requests that application or that thread has. Okay, so yeah, if you want to learn more about it, you can check this paper. But how do we solve the problem? Essentially, we have inter-thread interference, which is uncontrolled in all memory resources, memory controller, interconnect caches. We're going to focus a lot on memory controller, but this can be actually, like the high-level ideas can be also applied to interconnect caches, as also many people have done it as well. So we need to control it. So that's not a rocket science. Design and interference-aware, QoS-aware memory system for that. So now the memory controller needs to resolve memory contention by scheduling requests, and how to schedule requests to provide high system performance, high fairness to application, and configurability to system software. Okay. So yeah, if you are interested, here's the paper that you can check. And yeah, and this paper, part BS, we're going to actually learn about it detail today. So that for this paper, actually, we got very interesting, surprisingly good reviews. I mean, not surprisingly in the sense that this work was not good, but surprisingly from the review committee usually, that they wrote very interesting things for this work. And some other works that I'm gonna actually talk about it on the second part of this lecture. That, we designed QS ever, memory scheduling for improving performance. This work, stage memory scheduling, actually has been proposed for heterogeneous system when we have the CPU and GPU on the same die, which puts the problem in another level, because now you need to deal with different characteristics of CPU and GPU, which is harder to do. Okay, so these works we're going to see in more detail today and next week. Okay, and so there are a lot of goals and constraints and many metrics, and systems are also getting more complicated. So memory controller in the end is getting more complex. So the future is that memory controller is critical to research, and they will become even more important, and which we need to work on it more and more. So with that, I conclude this lecture 10A. We can actually have a short break, maybe for only 5 minutes, until we switch the gear to the next lecture, and then we will continue. Thank you. Okay, I think it's time. Okay, now I will continue memory controllers, but with a much more focus on service quality and performance. I think I have 200 slides for 10B, but definitely we are not going to finish it today, and we should continue the rest next Thursday. So essentially, when we have shared resources, we're going to get to that, the problem of service quality. And shared resource design for multi-core system is very important. Like all systems that we have today, they have a lot of shared resources, like memory channels, like shared memory, shared last level cache, shared storage, so shared interconnect. So in the end, you need to deal with a lot of sharing that you have in your system. So the concept behind resource sharing is that instead of dedicating a hardware resource to a hardware context, we allow multiple contexts to use it. So in the end, that can provide better efficiency in the system, right? So there are a lot of example resources that you can think of, like functional units, pipeline, caches, buses, memory, interconnect, storage, and so on. So sometimes people try to, in order to provide good performance and let's say good predictability, they try to provide some isolation. Like they partition your resources in several partitions, and if these partitions are physically isolated, then potentially you don't have interference and you have predictability. But the other side of it is that you're potentially losing some efficiency in the system. First of all, there might be applications that they really want to benefit from all the resources that you have, and they can benefit, but you cannot provide that because of that rigid isolation that you have in your system. Or, for example, also there are applications that they are not using their partition frequently. So now you have the problem of underutilizations, which by resource sharing, we are trying to actually avoid that. But if we just do resource sharing without controlling, then we're going to run into resource service quality and quality of service, fairness, and potentially also low performance, as a result of that. So yeah, we already discussed about this, that resource sharing also provides throughput for us. And also resource sharing, can reduce communication latency, which is very interesting when we think about a shared memory model. So for example, if you are sharing some caches, like let's say L1 cache or L2 cache banks, then communication between two different cores can be handled through that L2 cache bank, for example. You don't need to go over a lot of communication or sending protocol between the core 1 and core 2, for example, such that they can communicate. So that's why actually shared memory model is very interesting when you want to operate in a parallel programming. When you are operating on one node, there are a lot of shared resources on that node, and you can actually potentially benefit from all these shared resources to accelerate the shared memory model. Make sense? However, there are disadvantages, and resource sharing results in contention for resources. When the resource is not idle, another thread cannot use it. And if a space is occupied by one thread, another thread needs to basically reoccupy it. So this sometimes reduces each or some thread's performance, which in the end can also cause a quality of service issue. So thread performance can be worse than when it's run alone, which we already showed also in our example with like GCC and MATLAB, for example. When they run together, GCC actually experience much more slowdown. So this eliminates performance isolation, inconsistent performance across runs. Like predictability is going to be questionable when you have shared resources. And so exactly, because thread performance depends on co-executing threads. So essentially uncontrolled, free for all sharing, that would degrade the quality of service, which causes unfairness and starvation. So we need to efficiently and fairly utilize shared resources. I should also say that you're going to discuss a lot of techniques that will improve, how we handle, quality of service and provide, manage our shared resources. But at some point, if you want to have a strong guarantee, on the performance, and you cannot tolerate any, let's say, quality of service loss or something like that, you may need to be more aggressive. So that's why actually having some sort of isolation, or at some point physical isolation, might really be needed. But you don't need to do that only. So you can actually combine isolation techniques together with these, techniques that they try to avoid, contention and controlled contention across the resources. So these different techniques can be actually also implemented together. So here is an example with shared caches. Like I will go very quickly because I think by now you can easily understand it. Like there are, we have thread 1 when it runs alone. It occupies L1 and also occupies some part of L2. And when thread 2, when running alone on processor core 2, it occupies L1 cache and some part of L2. But when you run these two threads together, basically T1 occupies L2 more than T2, and that can potentially cause the low throughput for the thread 2 here, because of unfair cache sharing. So that's why also people try to work on cache sharing as well, like how we partition cache across different threads. If we do static partitioning, like that physical isolation, like kind of quite rigid, but you can also do that partitioning dynamically, like in the sense that on the runtime, at runtime, depending on the use cases, you can partition your cache across different threads dynamically. But we don't have time to go over it, but you can also check this paper that discuss about cache sharing and partitioning in chip multiprocessor architecture. So basically, why unpredictable performance is bad? Because that's one of them is that makes programmers' life difficult. Like programmers may put a lot of effort to optimize the code, like understanding how we access the cache, try to and have a memory access pattern to utilize the cache better to get good performance. But in the end, the program may not observe good performance because of the fact that this application is running together with some other applications, and because of the sharing and uncontrolled sharing resources that we have, in the end, we're not going to get good performance. And this also potentially cause discomfort to user. So it can be also cause for some application, this can be actually undesirable. Like for example, you are operating on video playing, like playing some video, and you need to get some basically image rate, such that you can watch the video without any stop. So if the latency that caused in your system would violate that rate, in the end, you can also cause some this issue for the user. So then user interference may not be user interference. Yeah, user may not have a good what's the word? Okay. There is this very interesting word for that, user. Does anyone know? Can help? Like in our mobile papers, we write a lot about that. Anyway, I may remember it later. But then, today I'm a bit delayed. I don't know why, but my memory does not work well. So yeah, essentially, user may not have a good performance and from that system. And that can also make system management difficult. How do we enforce a service level agreement (SLA) when hardware resource sharing is uncontrollable? So so in any way, in many cases, when, for example, you are getting services from a cloud, for example, a server, you might actually get some SLA, and you're paying based on that SLA. And if that cannot provide that SLA to you, then we're going to run into issues. User experience. I was trying to say user experience. So this can actually cause overhead on user experience. It's not a hard word to remember, but for some reason it's just okay. So also, as I also discussed a little bit about it, resource sharing versus partitioning. So you can also think of, we can partition our resources, but that, partitioning provides performance isolation, which is unpredictable performance. But the problem is what I said, right? We are in the risk of, having underutilized resources. Or we are also in the risk of, okay, at some point we really want more resources for that application, and we cannot provide them. But we can also think of combining these two together. So we can design shared resources such that they are efficiently utilized and controllable and partitionable. So we don't have to decide on either of them. We can actually use the insight of both approaches and have them together in our systems. So then we have no wasted resource and quality of service mechanism for threats. Okay. Yeah, so here is also another picture that we have shared memory resources, and also here is the chip boundary, and at the off chip also we have a lot of sharing. And this can actually cause interference across different threads. So these are the slides that we already actually discussed in the previous part of the lecture, that essentially this inter-thread application interface can cause several issues in existing memory systems. And here are the results that you've already seen, regarding the MATLAB and GCC, that they are observing different unbalanced slowdown. And we discussed about the reason, that because of the stream and random memory accesses, and these micro benchmarks, and the reason that we have observing such behavior because of the FRF CFS memory scheduling policies. I think we already observed all of them actually. Okay, but just to give you some idea, this does not need to be only on the memory controller. So cores, we're gonna also look into it more when we get to the interconnect part of the interconnect lectures. But cores can be also, they can be connected through some network on chip. This network is to, provide communication across cores, or also communication from cores to the last level cache, LSC banks, and also the memory controllers. So assuming that, for example, these cores, they want to communicate with this node. For example, this node is a memory controller, right? So and these cores are running some streaming accesses, like a stream application with a stream memory access pattern. So they are sending a lot of requests, and if you use a routing algorithm to route your the messages in this fashion, like X, you go first X and then you go then Y. This is called XY routing algorithm. You're gonna see a lot of contention on the basically these vertical links here, right? And that can potentially cause the 3 orders of magnitude increase in latency for the cores that they are actually standing here when they want to communicate. So that's why actually it's not the contention problem is not only at the memory controller, which we're gonna see a lot, but in other resources like the interconnect, it can be also cause a lot of performance issues. Okay. Yeah, if you want to learn more on interconnect-based starvation, you can actually also check this paper. But we're gonna also get to that in our interconnect, and potentially, if we have time, we will also see these papers also. So here is again, use of Maslow's hierarchy of needs. And you can think of that lack of quality of service can be safety and security problem, essentially. So that's why providing quality of service is very much important, kind of at the backbone of the needs for many cases. Okay. So quality of service aware memory systems. So there are challenges. First is how do we reduce inter-thread interference? So if we can reduce interference, we should try to do as much as possible. So that would improve system performance and core utilization and reduce request serialization and core starvation in general. But then when you have inter-thread interference, how do we control it? Which can actually provide mechanisms to enable system software to enforce quality of service policies and while providing high system performance. And also, how do we make the memory system configurable and flexible? Because having that flexibility is important to provide fairness or throughput when needed and satisfy performance guarantees when needed. So there might be different applications and different scenarios that you want to obey, and having such flexibility is very important to have. So we can actually having this in two different ways. We like to categorize it as having a smart resources and dumb resources. So smart resources means that basically design each shared resource to have a configurable interference control and reduction mechanism. Like we have a lot of these resources that they are shared, like interconnect, memory controller, caches. How I can make that resource quality of service aware, such that can reduce and control basically interference. So that's the way we can make that resource smart in a sense. But you can also think of, okay, I have resources that they are dumb. So we keep each resource free for all, but then we try to reduce or control interference by injection control or data mapping. So we try to basically handle the problem at a different level, essentially. So all these resources that they have, they're going to operate as they are, like in a dumb way. They're not going to handle quality of service. But for example, we can have this source throttling to control access to memory system. So this source throttling has been also used in network also a lot. Like if a router, for example, getting a lot of requests from some user, or let's say some port, that at some point basically that router can say that, okay, don't send me that a lot. Can reject some of them. I can throttle some of these requests for the network performance. This can be also in other systems, if you think about it, like for example, when you have a GPU and CPU, like GPU cores usually generate a lot of requests, and CPU cores generate actually less frequent requests. And CPU requests are going to be actually stalled because of a lot of GPU requests that we have. So one way would be design the memory controller, interconnect, caches, like all these components are smart to handle that interference. But another way would be also, in order to handle it, just reduce the rate of the GPU. Like just, for example, you can think of reducing the frequency of the GPU core. You just reduce the frequency so that GPU generates less requests. So of course, maybe it's not a great solution, but you can, the beauty of this technique, this kind of technique, is that it would affect many components. So with a smart resource, you really need to do it for all components. But with DOM, and it might be very hard, but with that DOM resources scenario, you can actually have such techniques which can generally affect your quality of service. And of course, you can think of combining these two also, right? You can, because you may not be able to make all resources smart, because that might be very costly. So you can still think of combining these two techniques. Another way of doing it in a DOM resource is that, for example, QoS-aware data mapping to memory controllers. How you map your data to the memory controller would affect the interference that you're going to see. Or, for example, quality of service aware thread scheduling course. If there are some threads that they are generating a lot of requests, or for example, there are two threads that you know that if these two threads run together, we're going to see a lot of interference. So we can generate that, we can transfer that hint to the scheduler. And in the end, the scheduler, which can be OS, does not schedule these two threads together, for example. So that can be also the way that you can reduce contention at the source, which, as I said, it has its own merit. And we should really also consider this approach in order to design, you know, a holistic and effective technique. But today we're going to see a lot on the QS-aware memory controllers. And so the goal is to reduce control inter-thread memory interference by one way is through prioritization or request scheduling. And so there are basically 4 fundamental interference control techniques based on what we have discussed, these smart resources and dumb resources. One way would be prioritization or request scheduling, which essentially makes the resource more resource smart. Another way would be data mapping to banks, channels, and ranks. For example, you can have kind of channel partition, which you know, avoid contention across these 2 applications, which has its good and bad, right? So when you partition channels, you should be careful that you don't do it, you know, in a way that cause underutilization of channels, essentially. And also core and source throttling, as well as application and thread scheduling. So we're going to see a lot on the prioritization or request scheduling today and also next week. We're going to also see some techniques on the line of, you know, the 2 and 3rd and 4th technique, but less, you know, with less detail. If you're impatient, you can also check these talks and previous lectures from related to these topics. Okay. I should also say that it's not only CPU that generates a lot of requests for memory controller. We also have, you know, this, you know, we have this I/O interference that, so your input output also generates a lot of requests, and that's very much memory mapped using that DMA engine. So then you all actually have interference between CPU requests and also I/O requests. And it's very hard to handle both together. So in this paper, which unfortunately we don't have time to go over it, we try to look into this problem, you know, about CPU and I/O traffic and how to isolate using, you know, decoupled direct memory access. If you're interested, you can check. I think it's one of the optional reading in homework 2 as well. Okay, so now let's start. Any question? Okay. Let's see some technique on the QS-aware memory scheduling. This is the picture that you already seen. And so there are a lot of ideas through that, which you can actually consider these a few slides as the summary of different techniques that we're going to discuss. So for you later, if you want to see the summary, actually, we are not, you know, going over all these techniques. So some of them are not going to be you know, presented in this lecture. But if you want to learn more, you can actually also check the papers. But for those that we're going to describe, you're going to see a lot detailed explanation. So we don't need to go over all this summary now. A lot. Okay. A lot of works. So this is the first work that I'd like to discuss, stall time fair memory scheduling, which the problem, as you know, is unfairness across different applications. And this is you know, vulnerable to denial of service, essentially. So how do we solve the problem? We have, essentially the goal is to threads sharing main memory should experience similar slowdowns compared to when they are run alone, which is fair scheduling. Assuming that all these threads, they have similar, like same priority, you don't want to prioritize each of them. Then the idea is that I run if I run this application alone, that I will get some performance. When I run it with different other application, I get lower performance. So I have some slowdown rate. Maybe like I will slow down by 2 or 3 times, for example. So if I in this scenario, we want to be fair. So we want to have kind of equal slowdown across different applications. So all these applications that they run together compared to their alone execution, we want to have the same, let's say, slowdown to make it fair. So that's the one way of defining, you know, fair essentially scheduling. So this also improves overall system performance by ensuring cores make proportional progress. So the idea is to make basic memory controller estimates each thread's slowdown due to interference and schedules requests in a way to balance the slowdowns. So a DRAM system is fair if it equalizes the slowdown of equal priority threads. That's what we discussed it. And so for doing that, we actually define some metrics, some parameters, essentially. So we use this parameter, which is DRAM-related stall time. So the time a thread spends waiting for DRAM memory. So that's a communication we need to provide to the memory controller from the core, that this is the stall time causing because of the DRAM. And then you can actually calculate stall time shared, which is DRAM-related stall time when the thread runs with other threads. So this is kind of easy to measure, right? Because at runtime, this thread is running with some other threads, and you can actually, measure this stall time shared. But the difficulty is actually to calculate stall time alone, because this application now is not running alone, right? So you can also run it alone, like another copy of it alone, but that's obviously that's not the goal, because we are causing a lot of energy and waste for that. So DRAM-related stall time when the thread runs alone, and this is very difficult to estimate actually. So assuming we have this stall time alone, we can have a memory slowdown calculated by stall time in a shared divided by stall time in alone, which is kind of relative increase in a stall time. And having this slowdown parameter for each thread, then we can actually come up with this memory scheduling called stall time fair memory scheduler, STFM, which aims to equalize memory slowdown for interfering threads without sacrificing performance. So it considers inherent DRAM performance of each thread and aims to allow proportional progress of threads. Okay. So how we do it? So actually, this is a very interesting idea. I like the idea, but it's not very easy to implement. And we're going to also see why it's not easy to implement. And later on, actually, we have done works to make it more implementable, essentially, which we're going to see also some works in that line, but probably next week. So for each thread, the DRAM controller tracks stall time shared and also estimates stall time in the alone way. So for the alone, basically, you need to read the paper to know details about how we estimate. But you can think of in a way that we can measure stall time in a shared mode, and then we can also estimate stall time because of the interference. Like for example, in the memory controller, there are some other requests that the thread A request is not scheduled because there are other threads going on. So once we know that information at the memory controller, you can actually add some or reduce some stall time from the stall time shared to get the stall time alone. But of course, now the question is that how much you're going to reduce that, So because partly these times are going to be hidden or kind of be overlapped, so it's not easy. And also, that's not the only reason that interference can cause the issue. That what would the effect of row buffer hit, basically, So there might be some other requests that you're experiencing higher stall time because you don't get row buffer hit rate in the data. So there are many different scenarios which this paper actually tries to discuss them and provide solution or kind of estimation for each of them. But of course, it might not be also perfect in many of some of these cases. Yes. Well, that is kind of considered in the DRAM stall time. because that application, when it's compute bound, is the DRAM stall time is also much lower, for that. So we are trying to handle that from that point of view. But yeah, potentially there can be many other reasons, that can cause. The paper actually discussed a lot of these things, and I can refer you to the paper. But in the end, that estimation is not perfect, and that's partly, the reason that implementing this technique is not easy. But if you have that estimation, and then you have this also stall time in the share, then you can compute the slowdown by this dividing the stall time in the share by stall time alone. And then you can compute unfairness based on the maximum slowdown that you have across all these applications divided by minimum slowdown. So you have, for example, 4 applications. For each of these applications, you calculate the slowdown, and then you divide the maximum slowdown by minimum slowdown. So ideally, you want to have 1, right? Meaning that maximum slowdown and minimum slowdown are equal. But if you have larger numbers than 1, then you are scheduling unfairly, assuming the metric that we have here. So then you can actually define some threshold. If unfairness is less than a threshold alpha, then use a DRAM throughput-oriented scheduling policy, meaning that you are still fair. But at some point, if your unfairness is greater or equal than threshold, this threshold can be also set by the system software, for example. Then you can you need to map to the mode which you use fairness-oriented scheduling policy. So requests from thread with maximum slowdown, we will first schedule them. And then after that, we're gonna get to the, the FRF-CFS, the row heat first and all this first. You can actually see with this example. So essentially you start, because your baseline scheduler is actually FRF-CFS. So you schedule thread 0. And again, you have requests from thread 0, which have row buffer heat, so you will schedule it. So by doing that, actually thread 1 is experiencing some slowdown, and you are actually measuring that, So now you can see that thread 0 does not experience any slowdown, but thread 1 is experiencing some slowdown. And then unfairness is 1.03, but the threshold is 1.05, meaning that until the unfairness lower than 1.05, I will keep doing it in a throughput-oriented way. So you do that until that thread 1 slowdown is bigger than, the unfairness is bigger than this threshold. Then you try to schedule a request from thread 1. Because that's the application that experienced the maximum slowdown, right? So you schedule a request from thread 1. Now the slowdown for thread 0 is also increasing. And as a result of that, unfairness actually has been changed also. Now you get back to the throughput-oriented way. So you, again, keep scheduling essentially the thread 0. Make sense? Okay. Okay, so upside, the first algorithm is specialized for fair multi-core memory scheduling that provides a mechanism to estimate memory slowdown of a thread, and good at providing fairness. Also, being fair can improve performance because of also the fact that we discussed. Like sometimes it's important to schedule requests of these applications because because this application does not generate a lot of requests, if you think about it. And then the processor can be actually optimized, can be utilized better. So if you service those requests, that processor can be utilized, and then you're going to have overall better performance as well. So it's not, you don't need to decide between either fair or low high performance. So sometimes when you are doing fair scheduling, you're also providing better performance as well. But of course, it has several downsides, like does not handle all types of interference, which we're going to see later also, and complex to implement. Slowdown estimations can be incorrect, which later on we try to actually make it better in a work that I will describe it next week, named MICE. We try to actually to improve the estimations of a slowdown, but in general, it's not easy to implement. Okay, any question? So if not, I will continue with this work, part BS, which is a very exciting work. It's one of the interesting work that I also love it, and has been also implemented in the industry SoCs. I think Samsung, they have realized that this is very interesting, memory scheduling policy, and they have adopted a version of it, some variant of it in their system on chip design. So in part BS, we try to focus on another problem that cause memory interference. So essentially, you do a lot at the processor chip to tolerate the latency of DRAM requests by benefiting from memory level parallels. Like you have this out of order execution and MLP, which they are there in order to tolerate the latency of DRAM requests. However, DRAM controller basically needs to be aware of that. So effective, all these techniques like MLP and out of order execution, non-blocking caches, run ahead execution. I mean, all these techniques that we already discussed also. I mean, some of them we didn't discuss in this course because they are kind of basic to computer architecture. But some of them, for example, with run ahead execution, we have discussed it. So all these techniques are effective only if the DRAM controller actually services the multiple requests in parallel in DRAM banks. So yeah, essentially the processor sends a lot of memory requests, like in the memory level parallelism. But if the memory controller is not aware of that and tries to address them in a serial manner, then you are not going to get performance improvement, right? So multiple threads share the DRAM controller. DRAM controllers are not aware of the thread's MLP and can service each thread's outstanding request serially, not in parallel. In the end, you're not getting performance. So this, I'm going to show with some example that when we have single thread, so thread A generates, after some computation, generates 2 DRAM requests. And these 2 requests actually go to different banks. So we are considering that these 2 requests are going to different banks because potentially we can address them in parallel. If they go to one bank, then we have, unfortunately, we have this, bank conflict, which that's why actually, that work that we discussed, subarray level parallelism, SALP, it comes to play, because that work we try to avoid the bank conflict as much as possible. But in this work, we are assuming that, for example, like in this example, we are considering that these 2 requests are actually going to different banks. So you're actually in current system, you're potentially capable of parallelizing these 2 DRAM requests nicely because they are going into different banks. So the first request goes to bank 0, and the second request goes to bank 1. So you can actually issue both requests almost at the same time. And then you're going to be stalled for some time because of these DRAM requests. But then at some point, you're going to get the result for both, and then you continue your computation. So that's the performance that you can get, for example, for this with MLP that generates 2 DRAM requests. Yeah, exactly. So because the bank latency are very much overlapped when you have this bank level parallelism. But if you have essentially 2 applications, A and B, and then the memory controller is not aware. So both of them, they generate 2 DRAM requests after some computation. And assume that these requests actually arrives at the memory controller level in this order. And this is not, this can easily happen because you have a network and you are issuing these requests through the network, and these requests needs to go through the network until they get to the memory controller. So they're going to experience different latencies. So in the end, memory controller can actually get these requests at a different time, essentially. So memory controller will receive requests from thread A first, and then 2 requests from thread B, and then 1 request from thread A. So now that what happened is that the memory controller issues the request from thread A, bank 0, row 1, and then moves to the thread B because there is no bank conflict here, right? The memory controller said, okay, I have another request from thread B, which goes to another bank. So sounds good. Let's schedule it. So memory controller schedule it to the bank 1. And after that, when we are after some time, when we get the, the results, basically when we are done with the bank 0 to service the request from thread A, memory controller starts scheduling the request for the thread B. And when we are done with bank 1, we can also schedule the request for the bank 0. And then basically after some time they can compute. So now you can see that even though we use MLP, and these applications, they could potentially benefit from MLP, and they hide or overlap bank access latency mostly, but actually we are servicing these bank access latency we are servicing the completely in a serial manner, which is not good. Like we are able to do it in parallel because they are going to different banks. So the scheduler, the memory controller scheduler, when it's parallel aware, can actually try to handle it by saying that, okay, so I have a request from thread A, which goes to bank 0. But then by having this insight or idea that this thread A actually might have some other request, this can actually also check the queue. And basically, memory controller now can understand that it's good to prioritize thread A, over thread B now, because I can benefit from the memory level parallels essentially. So then memory controller can issue, the request for thread A, bank 0 and bank 1. And so now the problem is, basically now there is no problem. Thread A is now happy. And basically you issue both at the same time and they overlap, and then you can start compute. Thread B, unfortunately, still needs to wait because, that's how it is. But when thread B also wants to do the basically the memory operation, you are benefiting from this bank level parallelism. But in the end, this leads to some safe cycles for application A, and not much different from application B. And your effective performance or average performance would be increased. So that's how the scheduler, when it's aware of the parallelism of the threads, can actually help us to get better performance. Make sense? Okay. So that's the work, PAR-BS, which is based on two principles. Principle 1 is that parallelism awareness, schedule requests from a thread to different banks back to back, which preserve each thread's bank parallelism. But this can also cause a starvation. If that cores or thread generates a lot of requests in a parallel, then it can starve other cores. So that's why we have principle 2, which is request batching. So we try to create a batch, and in that batch we group a fixed number of oldest requests from each thread into a batch, and we service the batch before all other requests, and then form a new batch when the current one is done. I'm going to show it with the example, which is going to be understandable much better. So that eliminates starvation and provides fairness and allows parallelism awareness within a batch. Like here, for example, you have 2 banks, and here are the requests from different threads, like thread 1 to thread 0 to thread 3. So essentially, you create a batch, and within this batch, you try to schedule requests. So in this example, actually, we have we have bank level parallelism for all these threads. So we don't need to do much within the batch. So basically, we prioritize. We schedule thread 0, and then we schedule thread 1. In between, we may receive some requests from thread 2, but we don't schedule them because we are operating on this batch, right? So we keep scheduling, until we are done with this batch, and then we create another batch, and then we continue scheduling those. So this can provide, better fairness and also improve performance, which is partly is also very. So to give you more detail, like PAR-BS has 2 components: request batching and within batch scheduling, which is within batch we need to be parallelism aware. So request batching is each memory request has its bit marked, which we mark it as associated with it, And then we have this batch formation. So we mark up to marking cap all this requests per bank for each thread, meaning that we have this batch size. If I want to, keep it simple, so we have a batch size. So we add some marking cap all this requests to that batch, and mark requests constitute the batch, as I said, and form a new batch when no mark requests are left, essentially. And mark requests are prioritized over unmarked ones. So no reordering of requests across batches, essentially. No starvation and high fairness. But actually, yeah, exactly. That's not the hardest part. So how this is the problem, like how to prioritize requests within a batch, like internally inside the batch, how we do the scheduling. So within batch scheduling, we can do different scheduling. So we can use any existing DRAM scheduling policy. It can be, for example, FRF CFS. But we also want to preserve intra-thread bank parallelism, as we already discussed, in order to service each thread's request back to back. And the way we do it, we try to handle it with by ranking of the threads. So we rank the threads, and then there are some threads with higher rank, and higher ranked threads are prioritized over lower ranked ones. And this improves the likelihood that requests from a thread are serviced in a parallel by different banks. I think I will show you with some example. Like ranking is easy, but the way that we do ranking, like in this case, for example, we rank thread A, and with that we try to service requests from thread A first and then B, so that we can benefit from parallelism. But how do we ranking? So essentially, ranking scheme affects system throughput and fairness. Like how do you rank threads to maximize system throughput and minimize unfairness, to equalize the slowdown of threads. So in order to maximize system throughput, we minimize average stall time of threads within the batch. So that's a key insight that we have here. So we want to minimize average stall time of threads within the batch to maximize the system throughput. And in order to minimize unfairness, we service threads with inherently low stall time early in the batch. Basically, the insight is that delaying memory non-intensive threads result in high slowdown, and that's what we already also discussed a lot. Like there are some if the threads is non-intensive, if we delay those requests, then that would cause a lot of slowdown. And it's actually based on this shortest stall time first, like shortest job first ranking, which also used in operating system, for example, to schedule threads and jobs. Shortest job first is actually very much important. And human beings also, we are doing that. When you start the day and you have a lot of things to do, usually you try to schedule shortest job, which might be eating breakfast, maybe, I don't know. Okay. Yeah, so this provides optimal system throughput, and which actually this has been proposed also a long time ago. And the controller estimates each thread's stall time within the batch and ranks threads with shorter stall time higher. Okay, so with this example, you can actually understand it quite well. So this shows a batch that we have requests from different threads and different banks that we have here, right? So what we do is we calculate two parameters for each thread. One of them is max bank load, and the other one is total load. So max bank load is maximum number of mark requests to any bank. So if you look at, for example, thread 0, you're going to see that thread 0 has only, like at most, it has one request per bank. So max bank load is 1. And the total load, like the total number of mark requests for thread 0 is 3, right? So we've added in this table. Then for thread 1, basically the max bank load is 2, and the total load is 4. So the idea behind it is that with max bank load, we rank thread with lower stall time, essentially. Because if one thread has several requests at that bank, meaning that those requests are going to be serialized, right? So that is not gonna have actually higher stall time. So now thread 0, since has only one request at most per bank, this can be actually addressed handled quite fast, because it can benefit from the parallelism, and so in the end, it's going to be shortest job in the end, right? So that's the idea behind this. That's why we are calculating max bank load, and the total number of mark requests also to break the ties, because there might be some cases that you have different threads with the same max bank load. Then you need a tiebreaker. For that, you basically break the ties based on the total number of memory requests that they have. So this is thread 1, and thread 2, for example, if you calculate, you're going to see the max bank load is 2, but the total load is 6. So that's why we are using this tiebreaker, which is total load. And thread 3, which is the worst one here, the max bank load is 5 and total load is 9, right? So now based on that, you can rank. So we are ranking thread 0 as the highest rank, and thread 1 and then 2 and 3. So this is the ranking. So in the baseline scheduling arrival order, this is going to be the way we schedule. So essentially, we're going to schedule thread 0. After some time, basically, this is the order that we receive all these requests, and thread 0 is going to experience the stall time of 4, and thread 1 is going to experience the stall time of 4 again, and thread 2 is going to experience a stall time of 5, right? And thread 3 also a stall time of 7. So this is the baseline schedule. However, in part BS, what we can do is solve it in a Tetris way. If you think about it, like now you can actually put all these requests from thread 0 in a block, and then schedule them first, because thread 0 has the highest rank. So now the stall time for thread 0 is 1. And the request from thread 1, you can actually also make another block in a Tetris way, and you put it like this, and then thread 1 is stall time is going to be 2. And thread 2 also, you can schedule it. Similarly, you're going to see the stall time is 4, and thread 0 is going to be stall time 7. So on average, you have 3.5 bank access latencies. However, in the baseline, it was 5 bank access latencies. Make sense? So yeah, let me quickly finish it, and then we will leave the rest for the next week. So PAR-BS scheduling policy is basically, when we put everything together, we mark the request first, and then we actually do row hit request first. You may say that this is actually against of parallelism aware, which is true, but based on our analysis, actually we observe that in the end is very good to prioritize row hit for better performance. But in the paper also we have results that we try to change the ordering of 2 and 3 and see the result. Higher ranked thread first, which is shortest stall time first, and then oldest first. So with marked request first is with batching technique, and the rest is parallelism aware within batch schedule. So there are different properties here, like exploit row buffer locality and intra-thread bank parallelism. And it's actually quite work conservative, because services unmarked requests to banks without marked requests. So that's that's a batching technique that helps us to not overcome to not cause starvation. However, marking cap, like batch size, is important. If you have 2 small batches, that can destroy row buffer locality, so you don't have enough number of requests in your batch, such that you can find a low buffer heat. If you also have 2 large gaps, then it can penalize memory non-intensive threads, because when they get to the memory controller, that memory controller is already operating on one batch, they need to wait for a long time until we are done with that batch. So the hardware cost of this technique is actually reasonably low, and it has no complex operations like divisions that we, for example, discussed in prior work to calculate the fairness. And it's not also on the critical path. The scheduler makes decision only every DRAM cycle, which is not that on the critical path. So we compare it against prior work, and we show actually very good performance and speed up across different prior scheduling techniques. So let me conclude with some upside and downside. PARBS is the first scheduler to address bank parallelism destruction across multiple threads. And it's actually a very simple mechanism compared to STFM that we discussed. And batching provides fairness. Ranking enables parallelism awareness. But at the same time also has some downside, like does not always prioritize the latency sensitive applications, which can be because of the batching scenario that we have. Can be actually harmful or not desirable for application which is latency sensitive, because they need to wait for that batch to be done until they can be scheduled. So if you're interested, here's the paper. It's also part of the reading, which you can check. And that brings me to the next scheduler, which we're going to cover next week. Sorry, we go a little bit over time, but I wanted to finish on a good, cut. Questions? Any burning questions? Okay, then have a nice weekend. I see you next Thursday.